my responsibility, as it says here, is everything telecom related to for Nvidia. What we actually are at such an amazing point in time, and some of us realize it, some of us may not, but multi-generational work can come together right now because we're talking about the inclusion of two amazing technologies, telecommunications and AI. This wouldn't have been possible 10 years ago in the formation of 5G, but it's something we should really take advantage of and not let it go by. And so with that thought in mind, let me just go through a few thoughts and a quick video.
For decades, telecom networks have been the lifeline of our world. Always there, always reliable. But now, we are at the tipping point for the future of communication. Telcos are evolving into something more. AI-powered grids that don't just connect. They think, adapt, and solve. Customer experiences and network operations are being reimagined with AI agents. AI factories are accelerating research, redefining innovation, and unlocking new possibilities for industries and nations. What were once simple relays are now AI powerhouses. Cell towers transforming signals into intelligence for billions. 5G and 6G are being designed, simulated, and trained with AI, making every connection smarter, every interaction more seamless. This isn't just an upgrade, it's a renaissance. Telcos are no longer just the backbone, they're powering what's next in physical AI, robotics, and beyond. AI is defining our future, and the future moves on telecom networks. The only question is, how far can we go together?
So I'll make a bold statement. There's never been a better time than now to be in the telecommunications industry. So what I'm going to talk about is some of the details behind some of that video and what we're doing to accelerate innovation, whether it be in research, in higher education research, which is a big focus for Nvidia, or within corporate research. We all know that every few years there's a new standard that comes around, and there's certain tenets that go into that standards formation. Not always do the standards that come out the other end reflect those tenets. But they're all, the right thoughts go in when we're getting the companies together, the vendors together, et cetera, and the telcos. And we're looking at things in the next generation, peak data rate, for instance, or I would say perhaps one of the most important aspects is spectrum efficiency. There's only a limited amount of spectrum available. Bringing out the maximum spectral efficiency, bringing out the maximum power efficiency, leveraging AI-enabled capabilities with sensing, environmentally aware networks. These things are very important, and we should focus on a few of these things rather than all of these things. Latency, I'll come on to maybe a little bit later. It's often a fallacy that you have to leverage network latency as the most important part of latency. As we go to intelligent networks, compute latency becomes a much, much bigger factor. And how do you organize compute latency such that you can take advantage of these new applications that may need the order of a second or so to have a reasonably realistic conversation with a digital human on a phone, when the network latency is 10 milliseconds only. There's new types of traffic. Traditionally, networks have delivered voice, data, and video. Going forward, the networks demand will also include AI traffic. Different types of traffic with different SLAs. that are required to service different types of endpoints. Glasses, of course, digital humans on phones. One of the biggest network demands is going to be driven by uplink from cameras. We're going to be already implementing video language models that sit either on a camera or near a camera. Video search and summarization by agentic AI flows will exist so that the network doesn't have to carry all the way data back to data centers. Now remember, just coming on to a point that Abdu mentioned earlier, power efficiency. There have been two parallel tracks that have started to emerge on power consumption. One is the power consumption for the radio access network. The other is power consumption for the accelerated compute or AI data centers. Why can't we merge those? Why can't we make much better efficiency? Why can't we do continuous improvement, continuous development in a software flow? Why can't radio access networks be software defined only? Well, they can, because now in this era of accelerated compute and AI, that becomes possible. These NIMs, as which we call them, which are Nvidia inference microservices, are lightweight serverless inferences that can be located at any point in the network, even on device, to incorporate these functions without the weight of the large language model coming along with them. So as our CEO said probably 2 weeks ago, next generation wireless networks will be revolutionary, and we have an unprecedented opportunity to ensure AI is woven in from the start. As I said, an amazing time to be in telecommunications. So how do we achieve this? Well, the concept of AI native wireless networks came around with AI RAN. What is AI RAN? Think of it as three fundamental, sometimes two, they get collapsed into two. AI RAN is AI and RAN. This is AI applications and radio access network running on exactly the same hardware infrastructure. No difference. Whether it be a small accelerated compute infrastructure that sits out on the base station, consuming 100 watts or less, or it be a larger AI infrastructure that sits within a CRAN implementation that runs pooling of AI infrastructure also. AI for RAN, I'm going to talk a little bit more about that. How do we leverage AI in the signal processing and the management layer? And then AI on RAN. AI applications delivered over a radio access network. Think of it as 5G, 5G advanced, 6G. And as we move through those Gs, they should be software upgrades, not complete system hardware upgrades. But AI running over the radio access network. Many telcos are using AI already. External AI workloads, internal AI workloads to improve productivity, and now adding to that RAN workloads or containerized network functions. All of these are software overlays on the same basic hardware infrastructure. SoftBank did an evaluation in their first implementation of this and found better utilization, better energy efficiency than these are than traditional networks. Performance, improved spectral efficiency, and software upgradable to 6G, whatever 6G may be. So the way we look at the world, Nvidia, is that we started off about 7, 8 years ago working on some fundamentally, I think, similar problems in telecommunications than we've done in every other industry. What is the complex computational layers that we can accelerate? And we found layer 1 in the 5G stack fit that very well. So we started about accelerating layer 1 in the 5G stack on a GPU. We see going forward not just AI and acceleration in layer 1, but also now adding in layer 2. And we'll show some examples of that. But layer 2, many functions in the traditional network stack, if you keep to the traditional network stack, And then going forward, in that line of AI foreran, we're seeing neural schedulers. We're also deep reinforcement learning within environments, integrated sensing and communication leveraging AI, and orchestration leveraging neural networks. What we've first shown, together with some partners, DeepSig and SoftBank and Fujitsu, is uplink speed and performance improvement, and also throughput gains by taking layer 1 elements and running those as a neural network that can be trained by the environment. So taking those traditional blocks and putting them into AI neural network. We were able to do this, actually. Multiple demos were showing, there were about 10 demos that were developed by the AI RAN Alliance, which was formed only a year ago and now has over 75 member companies, when it was formed by 10 companies a year ago. 10 demos were showing these types of real improvements on that accelerated infrastructure. So this is just one example of the simulated results of a neural network versus a traditional layer 1. And what you can start to see is in channel estimation, you can start to see on the right-hand side is the simulated world. I'll come on to that a little bit later. It's a digital twin of a real world with real buildings. On the right-hand side, on the left-hand side, sorry, is what we have running in a campus environment within Nvidia. The same thing, and looking at the live results on the accelerated compute infrastructure. You can see significant enhancements by optimizing through a neural network. So what happened about a week ago was that a few like-minded companies decided that we need to accelerate the research, development, and deployment of AI-native wireless networks. So Nvidia, together with T-Mobile, Cisco, MITRE, which is a government-funded research organization within the US, and the ORAN Development Company, which is part of Cerberus, a private equity company that's focused on ORAN stack development. We got together and we said, we're going to work on research, on AI-native wireless deployments, to actually accelerate how fast we can see some of these major improvement opportunities and take them into reality. At Nvidia, we see the world, you saw it earlier, kind of in as a three-computer system. A simulate, or a train, a simulate, and deploy model that is continuous learning and continuous improvement going through those cycles. As part of the train, we developed about 3 years ago, released on open source on GitHub, a differentiable layer 1 link layer simulator. It's had over 150,000 downloads, I would say mostly by academic research. We also have now received 280 paper citations that have using Shiona. We also announced our aerial, what we call our 6G developer program, and aerial are the tools that we include within our 6G developer program about a year ago. We now have over 2,000 members within that program. There's 58 universities in the US, and I think at last count, might get this number wrong, around 350 universities worldwide that are part of this program, taking access to these research tools. And somebody said earlier, should research participate more in standardization? Absolutely. Our goal is to democratize research, but give you the tools that you can really develop fundamental research to deployment. Part of those tools was an update to the Shiona 1.0, which now has extremely fast ray tracing implementation attached to that as an extension. Also, we moved to a more a system-level environment as opposed to just the layer 1. And we also announced the Shiona Research Kit, which is a small GPU, a Jetson GPU, that essentially you can now run an OAI stack on top of that GPU. There is a CPU in there as well. You can run CPU and GPU accelerated offload, and you can run that over the air. So not only can you simulate, but you can now deploy within a research environment for relatively low cost. We have worked, in Nvidia, we work with our ecosystem. We are dependent upon our ecosystems. On the Aerial Omniverse Digital Twin, which I'm going to show you some examples of, we have a number of partners that are developing EM solvers. We have our own EM solver in that environment, but developing EM solvers and developing tools and technologies that they are themselves taking out to market using Aerial Omniverse Digital Twin. We have now enabled that Aerial Omniverse Digital Twin on AWS and on Azure. You can run it on desktop. You can run it on PC. You can run it anywhere. That's our goal, is to make it ubiquitously available. At the same time, you saw earlier that Shiona Research Kit, the small Jetson. We have a version of that that can run massive MIMO and can be more, is a higher end version of that we call our Aerial Commercial Test Bed. You'll see the stack there. It's based upon our Grace Hopper 200 MGX server architecture, available from Sterling and Supermicro. It has an OAI open source layer 2 plus running on our Aerial layer 1. So what I thought I would show here is, traditional radio access networks have always required a very manual process for design. Using Aerial Omniverse Digital Twin, and this is a part of Berlin, we're able to operate within this Aerial Omniverse Digital Twin and deploy physically accurate scenes that can really comprehend the environment, foliage, the material properties of buildings, the weather systems, and the RF propagation is accurate with our EM solvers for reflections, refractions, etc. This is also includes a number, as you can see, of antennas and base stations. How do we do this? Well, first we start off with a 2D type floor plan of the environment, and we start placing UEs in the environment. And those UEs can move around. And then we start to, as we start to define the material properties of that environment, we build the buildings. We add the coats of the materials to the buildings. We add the foliage to the buildings. We have the UEs still moving around the environment. And once these scenes are built in what we call the Aerial Omniverse Digital Twin, we can start inserting RF into the scene as well. And this is physics accurate RF using EM solvers that have been ground truth sourced with real data. And then what we can do is start training the algorithms that in a simulated environment and start deploying them into the Aerial Omniverse Digital Twin. And as you saw earlier, what we're able to do then is use those trained algorithms and optimize them within the simulated environment. This is the power of a neural network and data collection within the neural network that you continuously optimize. We showed last week that one of our partners, SoftBank, was able to do this for a baseball stadium in Tokyo to simulate how would they optimize throughput and gain for the number of people in that baseball stadium. But once we've already seen that we can optimize, we can start to look at things like cell edge coverage. And then we can collect data and optimize for cell edge coverage, such that we can get much more efficient throughput and gain at those So now as people are connected to the environment, they're really experiencing the best, the most power efficient network. That's all I have. Open to questions. Thank you.